Chapter 14, Gas Mixtures. All right, class, today we're going to have a simple and friendly chat about gas mixtures, like how different candies get mixed in one jar. Imagine you have a jar filled with colorful candies. Some are red, some are green, and some are blue. The candies are like gases, each with its own identity. But when they are together, they all share the jar equally. In thermodynamics, when different gases are mixed, we still want to know how much of each gas is in there, how they behave together, and how we can predict things like pressure, volume, and temperature. First, we use something called mass fraction and mole fraction. Mass fraction tells us how heavy each type of candy is compared to the total weight in the jar. Mole fraction tells us how many pieces of each type there are. Even if some candies are bigger and heavier, in counting terms, we just care about how many pieces we have, not their weight. That's why mole fraction is like counting candies, while mass fraction is like weighing them on a scale. Then we talk about Dalton's law and Amagat's law, which are like magic rules for mixtures. Dalton's law says, if each gas was in the jar alone, how much pressure would it make? Then it adds all those pressures together to get the total pressure. Amagat's law asks, if each gas was alone, how much space would it take? And adds the volumes to get the total volume. For ideal gases, these two methods give the same answer, just like adding candies or counting their total weight. Now, we also care about energy properties, like internal energy, enthalpy, and entropy. Think of these like the happiness energy inside each candy. To know the total happiness energy of the whole jar, we simply add up the happiness energy of all the candies based on how many there are. The temperature of the whole jar is like the average mood. If all candies are at 25 Celsius, the whole jar is 25 Celsius. When we cool down or heat up the jar, the candies either lose or gain energy. We can calculate how much energy they change using simple formulas. For ideal gases, everything depends mostly on temperature, but for real gases, things get trickier, like candies sticking to each other or being squished inside the jar. That's when we need special tools like compressibility factors or K's rule, which give us clever shortcuts to still figure out energy and pressure. We also learned that when gases mix together, they naturally get more mixed up and create more entropy, which is like making the jar messier. This mixing is irreversible, meaning you can't easily separate them without extra effort, just like you can't easily take all the red candies back out of a mixed jar without sorting. Finally, we use all these ideas to solve practical problems, like finding out how much work a turbine produces, how much energy a cooling system saves, or how much entropy is created when gases mix. Even though it sounds complicated, we can always break it down into simple steps. Count how much gas you have, see how much energy it has, and use the magic laws to know what happens when things change. So next time you look at a balloon or breathe air, remember it's actually a colorful mix of different gases following these fun and simple rules. And now you know the secrets behind their behavior, just like a scientist.